Okay, so let's start. Recall that our goal is to efficiently design a binary classifier, right? So far, what do we know? We know how to design linear classifiers, and to design linear classifiers, we know of two techniques. One is the empirical risk minimization algorithm, which is in general computationally complex. It's a combinatorial problem which may be hard to solve. On the other hand, we have the hard SVM or the soft SVM algorithm, which we know can be implemented efficiently. And the hard SVM algorithm, if the data is linearly separable, just basically boils down to ERM, right? Again, when I say ERM with respect to the 0-1 loss. That's the loss that we're interested in minimizing, actually minimizing, right? But well, the problem with linear classifiers is that we know how well linear classifiers perform, in the sense that we know that the generalization error, at least if using the hard or soft SVM algorithm, we know that they can achieve a generalization error that is close to the best possible linear classifier, right? But as we know, the generalization algorithm of any classifier or any learning algorithm is can be decomposed in the following way. So it's the risk of HS, which is the output of the learning algorithm using samples S, minus R of H star, which is where H star is the best possible hypothesis from your class, plus R of H star. Whether you use ERM or you use hard or soft SVM, you can make this as small as possible by increasing the number of samples. But then the approximation error, which is R of H star, that may be fairly large because your classifier is not expressive enough, because it isn't rich enough. So linear classifiers aren't going to cut it for many problems of interest. So you need to go to non-linear classifiers. But so far, the only algorithm that we know is ERM, right? We don't know of any efficient algorithm to train a non-linear classifier so far. And that is where kernel methods can help. It doesn't mean that you can design an arbitrary or train an arbitrary non-linear classifiers. We're still going to look at a specific subclass of non-linear classifiers, and those for which you can learn using a hard SVM or a soft SVM type algorithm. Yep, it's a non-linear classifier. Yes. Again, typically you cannot implement ERM with respect to the 0-1 loss. So even when you're training classifiers, say neural network classifiers, you typically do it with respect to a different loss. For example, the cross entropy loss or some other kind of loss. Because ultimately, if, like, most learning algorithms are based on optimization techniques like stochastic gradient descent, for which you need to have a sufficiently smooth function to optimize over. Right? So it performs well if your loss function is smooth, and that's why people go to say like approximate the loss, the 0-1 loss, using a different loss function, such as the cross entropy loss. Right? So that's one sort of approach, right? Where you fix a hypothesis class consisting of nonlinear classifiers, and then you try to approximate ERM using different techniques. That's one particular approach. The other approach is to still try to utilize these hard SVM, soft SVM type algorithms, but somehow do them efficiently, and that is what brings us to kernel methods. Right? So in fact, let's look at the following example. Suppose now that I want to train a polynomial classifier. How can I write a polynomial classifier? So it is, first of all, again, let's assume that we're training polynomial classifiers for R. Okay, so h of x is of the form indicator function summation I equal to say 0 to k ai x to the power I greater than or equal to, right? So this is 0. Right, I'm looking at the constant. Fine, I agree. I could just have replaced started this off from 1 and gone all the way up to k, but not lose anything by doing so. Or if you want, let me just say is greater than or equal to 0. All right. Can you express this as a linear classifier? Or can you view this as a linear classifier? K is fixed. Correct. So basically, I could view this as h of x equal to the indicator function of A transpose the following vector, which is 1 x square all the way up to x to the power k greater than or equal to 0. Right? So you can view this as embedding x in a higher dimensional feature space, in a k plus 1 dimensional feature space, and then training a linear classifier. Right? It's a specific instance, but at least we're confident that we can train a polynomial classifier just using the ideas of linear classification. I can use the linear classification, the soft SVM algorithm to train a polynomial classifier. But as I mentioned in the previous class, if you take k to be large, then your VC dimension increases, because what is the VC dimension of a polynomial classifier? It's k plus 1, and therefore the number of samples that you require and the complexity that you require to train the algorithm is also going to scale with k. Right? So you can view this as a particular type of embedding in a higher dimensional space in order to convert a non-linear classifier to a linear classifier. When viewed in the higher dimensional space, it looks like a linear classifier. So firstly, the first thing that we're going to look at is it possible to reduce the computational complexity? Right? Otherwise, there's nothing else. There's nothing else to be done, right? Because I just find a suitable embedding and then just train a classifier in, say, k dimensional space. Sample complexity is also high, but again, let's leave sample complexity aside for now. Suppose that we have enough data. So data is not really the bottleneck, but computational complexity is still a bottleneck. If I want my hypothesis class to be rich enough, then I should choose k to be sufficiently large, but that means that my computational complexity is also going to be large. The first step to take is try to reduce the computational complexity. And it turns out there is a way to reduce the computational complexity. And why is that? It's because we're looking at a specific algorithm. We're not implementing ERM. We're trying to implement a soft SVM. Right? So and the nice feature about the soft SVM is the following. So what would soft SVM look like for in the feature space? What is optimization algorithm? We want to minimize overall possible A, in, say, Rk of the 2 norm of A whole square plus 1 over n summation I equal to 1 to n, the hinge loss, which is nothing but max between 0 and 1 minus yi times the dot product between A and, we're now looking at the feature space, so it's going to be psi of xi. Right? Okay, this doesn't seem like we can reduce the complexity, because after all of this whole optimization problem is in k dimensions. But what do we know about the soft SVM? What does the solution look like? Some linear combination of these psi of xi, right? So summation I equal to 1 to n times some alpha I psi of xi. So that's something that we know. And let's assume that we are in fact trying to train a homogeneous classifier, in the sense that B is always set to be equal to 0. Right? That reduces one variable, but let's say that that's what we're trying to do. Then what is the class? So suppose I'm given a new sample. What do I need to do? I need to just check. So H A star of X is, how do you, what do you do? You declare 1 if psi of X, if the inner product between psi of X and A is greater than or equal to 0, and declare 0 otherwise. Correct? But A is just a linear combination of the psi of xi's. So I can say that this is equal to summation I equal to 1 to n. Again, it's a linear combination of the psi of xi's, and you have the linear property of the inner product. So this is alpha I times inner product between psi of x and psi of xi. If this is greater than or equal to 0, then I declare a 1 and I declare a 0 otherwise. So let's say that I have some magical way of finding the alpha i's. I'm able to solve this optimization problem. Then I don't really need to know what psi of x is and psi of xi is. If there is some way of being able to compute inner products between psi of x and psi of xi, that is sufficient. The only information that I need to know about psi of x and psi of xi is what their inner product is. The brute force way is, of course, I do the actual, I transform each x to psi of x, xi to psi of xi, and then compute the inner product, which means that the computational complexity involves the transformation plus I have to compute the inner product in Rk, so that's linear in K. And I need to do this for n different vectors. But if we can compute, we can efficiently, let's say, compute the inner product between psi of x and psi of xi each x1 through xn and every x efficiently in a computational complexity which is much less than k, or k times, yeah, uh, if you can compute it in time much less than k, then it's good. Right. But it's not evident how to do this, right? So that's the whole idea behind kernel methods. You don't really explicitly design the embedding, but instead you try to find an embedding for which this inner product can be computed efficiently. Design psi, so to speak. We don't ultimately we won't really explicitly design psi such that the inner product right, can be computed efficiently. And in fact, I'll be more ambitious. I won't simply restrict myself to k-dimensional spaces. I may want to embed it in a, let's say, an infinite dimensional space. For instance, if I want to say design a polynomial classifier where I'm looking at the space of all possible polynomials of all possible degrees, I still want to be able to do it efficiently. All right. Now, learnability is a different story, right? Because we know that the set of the classifier consisting of the set of all polynomials has infinite VC dimension. But again, let's leave aside learnability and only focus on computational efficiency for now. All right. And we'll see that it can be done. We can train a polynomial classifier quite efficiently. Okay, so let me define what a kernel is. So effectively, we won't design explicitly design the feature map. We'll design these so-called kernels, which play the role of this inner product. So any function k that takes two elements from the domain and outputs a real number is called a kernel. That's a general definition of a kernel, but there are, I mean, depending on which reference you use, this any function may or may not be called a kernel. But really what we are interested in are so-called positive definite symmetric kernels. So a kernel is PDS. Again, it's bad terminology, unfortunately. Positive definite symmetric if it satisfies the following property. If So you take any set of M vectors and you form the following kernel matrix. So it's called a kernel or a gram matrix. So it is this matrix where the ijth entry is k of xi xj. So it's positive definite symmetric if this is symmetric and positive semi-definite. So even though it's called a positive definite symmetric kernel, uh, the requirement is that the gram matrix or the kernel matrix is positive semi-definite. Unfortunately, this terminology is standard. It would have been better to call this positive semi-definite symmetric kernel. Again, depending on which reference you see, some references call PDS kernels simply kernels. The definition of a kernel is basically a function from x cross x to R, such that the gram matrix is always PSD for every set of M vectors. All right. Some references choose to distinguish between like general kernels and PDS kernels, but really what we are interested in are only PDS kernels. It should happen for every set of M vectors in the domain. Okay. Let's see why this requirement is needed. Suppose that k of x1, k of xi, xj is in fact an inner product. Okay. So let's take the following example where k of xi or k of xx prime is in fact a valid inner product. Okay. What can you say about the gram matrix that's obtained from k of x prime? Is this going to be PSD? Okay, so firstly, is it symmetric? It's going to be symmetric because k of xi xj should be equal to k of xj xi just by symmetry of the inner product. Can we say something about whether this is positive semi-definite or not? Let's consider a 2 cross 2 case. Okay. So I have x1 inner product between x1 and x1, inner product between x2, x2, inner product between x1, x2, and inner product between x2 and x1 or x1 and x2. Okay. Claim is that this need not be PSD. All right. What we want to show is that this is PSD for every single x1 and x2. Right. How do you go about showing whether this is PSD or not? 2, 3. Okay. How can you say that 2332 corresponds to a valid inner product? Okay, so can you find two vectors, x1 and x2, such that their what is x1, the inner product between x1 with itself, the two norm squared of x1, right? What can you say? Can you get two vectors for which the two norm squared is 2, but the inner product between them is 3? In fact, you can't. Think about it later. All right. Okay, so K transpose XK should be greater than or equal. I mean, X transpose KX should be greater than or equal to 0. Right? Okay, how do you verify in this case? What would that? So let me. The dot product between x1 and x2 need not be greater than. Again, why is that required? The vectors will make it. Okay. So first, maybe let's take a step back. Let's try to see what the determinant is going to be. If it's PSD, then what should be? I divide by the norm square of it. Okay. So, like it's a positive term multiplied by a matrix and getting divided by the norm. So in a way, forcing them to be unit vector. Forcing which one to be unit vectors? Now we can think that the matrix. Okay, x1 and x2 are unit vectors. Okay. So the diagonal entries are what? Fine. And the off diagonal entries would be some a. It will be 1 to minus. Okay. And if we take the determinant of that, that would be 1 minus a square. Okay. Which forces the 2 correct. But also it reduces to something that you're kind of. So what is the determinant of this equal to? This is equal to norm x1 square, norm x2 square minus the inner product between x1 and x2 square. Okay. Now suppose that this is greater than or equal to 0. Okay. Greater than or equal to 0 means that inner product between x1 and x2 should be less than or equal to norm x1 times norm x2, which is just Cauchy-Schwarz. That's another way of saying that, okay, the determinant is always non-negative. So effectively what you've shown is a proof of Cauchy-Schwarz inequality, right? Okay. Which one? No, it's not sufficient, necessary, right? So let's look at X transpose AX, or let's say alpha transpose, say alpha 1, alpha 2 times inner product between x1, 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 x2, x1, 2, x2, x2, alpha 1, alpha 2. What does it evaluate to? The determinant is positive. You can also see that the trace is positive. The trace is also positive. So, yeah. You can. But what I want is a more general idea. That's why I want to go about expanding this whole thing out and seeing what it looks like. Okay. Great. So what does this boil down to? What does it look like? Or let me try to do this more generally. If I take, say, vector alpha times matrix K alpha, what is this equal to? No, I just want to expand it out in terms of the ith element of K and the ith element of alpha. Okay, so it's alpha I, alpha j times the Kij. But what is Kij? Okay, xi, xj. Okay, which is also equal to I equal to 1 to n, j equal to 1 to n, in a product between alpha I, alpha j, xj. Okay. Now let me use linearity of the inner product. Let me, for each I can fix a particular I, and I can take this whole summation inside. So I get, let me move this, right? So this is summation I equal to 1 to n alpha I xi, summation j equal to 1 to n alpha j xj. Now this is some vector, and I have a linear expression in terms of the alpha I xi's. So this is equal to summation I equal to 1 to n, I'm sorry, inner product between summation I equal to 1 to n alpha I xi and summation j equal to 1 to n alpha j xj, which is what? It's just the 2 norm square of summation I equal to 1 to n alpha I xi. Which is greater than or equal to 0. Right? So if k of xi xj is actually an inner product, it doesn't matter whether this inner product is in R, Rd, or even over an infinite dimensional space. As long as I have an inner product between vectors, the corresponding gram matrix is always going to be positive semi-definite. Question? I'm sorry? A kernel defined by an inner product is PDS. A part of which definition? So again, it depends on which reference you follow, right? According to certain references, so a PDS kernel is simply called a kernel, which means that for a function from x cross x to R to be called a kernel, the gram matrix should always be symmetric PSD. Okay. In this course, we'll refer to these as PDS kernels, just to be explicit. Okay. Sometimes we'll just refer to them as kernels, but again, throughout the discussion, we're only going to talk about PDS kernels. Okay. Yeah.
So should be true for arbitrary.
Yeah.
And suppose if a kernel is positive,
It's PDS.
yes, for a particular, suppose for m naught till m naught, we know that for if we take any set of vectors,
Okay.
it's like a corresponding.
Okay.
Can we prove that it would be true for m naught plus?
May not be. I mean, just for instance, go from 1 to 2.
Like one is a different case, but
Yeah.
apart from one.
Yeah. In general, that may not be true. So we must show that the corresponding Gram matrix is PSD for all M. Okay.
So I compute the end product helps us evaluate the map.
Correct. It helps us evaluate the map, and as we'll see later, it also helps us find the corresponding SVM efficiently. It does. So we'll come up with an optimization algorithm, or we'll come up with a training method in order to such that the computational complexity doesn't scale with the dimension k. So we should be able to train using complexity that is independent of k, and we should be able to evaluate using complexity that is independent of k. Okay, that's the main goal. Okay, so first let's see some examples of kernels. I'll just give you the examples and then we'll go ahead and try to prove whether these kernels are PDS or not. So the first is exactly what we've seen, what's sometimes called the linear kernel. That is k of whatever x comma y is simply the inner product between x and y. We know that this is a PDS kernel as we've just shown. Okay. The second is the so-called polynomial kernel. Which is okay. So even before that, go back to the let's go back to the linear kernel. This linear kernel corresponds to a particular feature map. What is the feature map? It's the identity map, right? It's a trivial identity map. So let's look at the polynomial kernel. I'm right now I'm going sort of backwards, right? Instead of first defining a feature map and then trying to find out what the inner product looks like, I'm trying to first define a kernel which is supposed to be my inner product and then trying to see what the feature map would look like. So what is so k of x? Again, let's do it for r. So k is from r cross r to r, and it's defined as follows: k of x prime is simply equal to 1 plus x prime whole to the power let's say k. Okay, this is how I define. In general, it's going to be if I want to look at vectors x over r to the k, this is going to be defined as 1 plus inner product between x and x prime whole to the power k. Okay, let's just focus on R because that's simple enough. What hyperparameter? K is fixed, yeah. So again, when I say polynomial kernel, we'll see why that's called the polynomial kernel. I want to find the feature map. Once you find the feature map, it will be clear where that k comes from. So I want to express this as an inner product between two vectors, one containing x and one containing x prime. Or in other words, I want to write this as inner product between psi of x and psi of x prime. Any guesses what we can do?
You just take away from X when actually on the
Okay, that's good. What does it look like? Just take the binomial expansion, summation I equal to 0 to k. What is the binomial expansion? Okay, so it's going to be k choose I times going to be whatever this raised to the I times this raised to the k minus I, which is nothing but x prime whole raised to the I. I want to write this as an inner product. What is it? How would I be able to do that? So these are k plus 1 I want to write this as the inner product between two k plus 1 dimensional vectors. Okay, but then I have this k choose I, right? I want to write this as the standard inner product between two vectors in k plus 1 dimensions.
yeah, I think each comes as a polynomial.
It's going to be monomial, right? The ith component is going to be x to the power I. I have only one k choose I. Square root of k choose I, right? So I can just write this as summation I equal to 0 to k square root of k choose I times x whatever times x to the power I times square root of k choose I x prime to the power I. So my psi of x is going to be 1 square root of k choose 1 times x square root of k choose 2 times x square and so on. Right? So that's now you see why it's called the polynomial kernel. It's effectively you're mapping x to a polynomial of degree k. The coefficients are not, or in other words, the ith component is the ith monomial of degree I. But the coefficients are not exactly equal to 1. They're all different. They're chosen this nice way. Okay.
What should be what should be
I'll leave that to you as an exercise. Right. This is in sort of a standard form. So that would be a standard form for the embedding or the feature map. But this is a much nicer form for the kernel. Something that you can compute more efficiently, particularly when you go to higher dimensions. All right. So clearly this is the polynomial kernel is in fact an inner product between two vectors of a higher dimension. So it is a PDS kernel. Right? That you're convinced by that? Okay. Correct. It is the inner product, but what do I need in order to be able to compute this? I just have to compute 1 plus x prime whole to the power k. Right? X is in R, but in general, again, then we're looking at, let's say, R to the D to R to the K, right? In fact, not R to the K is going to be much larger. I have to only compute inner product in R to the D and then raise that to the power K. Can you repeat? The final value that you get is the same, but your computational complexity is much lower because you're not doing your computation over R to the K, you're effectively doing it just over R. But in fact, again, I'll leave it as an exercise. Just try to think about what dimension K of x prime, I mean, if you look at the embedding or the feature map from x, from vector x to some higher dimensional space, what that dimension is going to be. It's not going to be K, that's a hint. Okay, so just as we did here, so in this case, my D was equal to 1, correct? In this example that we did over here, so K is from RD cross RD to R, let me call it, let's say RK, okay, and K of x prime is equal to, say, 1 plus inner product between x and x prime whole to the power p for some positive integer p. Now this corresponds to some, again I claim that this is going to correspond to some feature map from R to the D to R to the K. From R to the D to R to the K, for some K. What is that K going to be? Is it going to be equal to P in general for general D or not? Correct. Yes, that's the question. So this corresponds to some psi from R to the D to R to the K. If D is equal to 1, then we've seen that P is equal to K. When D is not equal to 1, what happens? I claim that it's not going to be R to the K. I claim that K is not going to be equal to P. Okay. Again, I leave that as an exercise. Right. So that's another example of a kernel. What is very frequently used in practice is a so-called Gaussian kernel. That's defined as follows. So k of x prime is e raised to minus 2 norm of x minus x prime square by 2 sigma square. Okay. I claim that this is also a PDS kernel. We won't immediately see, I mean, just in a little bit, we'll see what kind of a feature map this corresponds to. Okay. And we'll see why this is a PDS kernel. Another is the, okay. So all of this is from some r to the d to r to the p, right? But in general, you could define, I mean, if you look at the definition of a kernel, the domain doesn't have to be Euclidean. It doesn't have to have any sort of an inner product structure. Right? It could be an arbitrary map from some set to R2, but it maps to something in a vector space. Right? The output, yeah, the output of the kernel is a real number. No, right? It need not be positive. The inner product need not be positive, right? Could be negative. Right? I mean, even here, I mean, if you take, say, k equal to 3, x and x prime could be arbitrary real numbers. So just take x to be equal to 2, x prime to be equal to minus 2, you get a negative real number. Same holds true for this. But of course, the Gaussian kernel is special in that sense. It's never negative. Always non-negative. Yeah, we'll revisit the Gaussian kernel in a little bit, but first we'll see an example of a kernel from a different set. So this is the sequence mismatch kernel. So this is, in this case, x is the set of all sequences of arbitrary length over some finite set. For example, it could be set of all binary strings. Okay. Again, sequence, when I say sequence, it means it has finite length, but the length could be arbitrary. So it could be, so it could have k of 0, 1, 0, 0, 0, 1 along with just 1, 0. Two sequences need not have the same length, but they're all of finite length. Right? So the sequence mismatch kernel, it basically outputs the number of common subsequences between these two. X prime is basically the number of common subsequences. So what do we mean by a common subsequence? Right. So it's any sequence in the same order that appears in both strings. So for example, 1 0 is a common subsequence. 1 0, 1 0 appears in both. 1 1 is a common subsequence because I have 1 1 and I have a 1 1. But there are different ways of, there are different common subsequences because this 1 1 and this 1 1 is a common subsequence. At the same time, this 1 1 and this 1 1 is a different common subsequence. Right? Yes. In general, the number of common subsequences is going to grow exponentially in the length of the shortest sequence. Or sorry, it would grow exponentially in the length of the longest sequence. Okay, so this is so k of x prime is the number of common subsequences, and my claim is that this is a PDS kernel. Right? We won't prove that here. But one feature that you see in all of these cases is, okay, it's a map from some arbitrary domain to or it corresponds to some feature map from an arbitrary domain to Euclidean space of some dimension. But at the same time, this kernel should also kind of measure similarity in some sense. Right? If the inputs are close, then the kernel should take a reasonably large value. If they're very, very different, then it should take a very small value. And let's see if that happens in each case. The inner product, of course, that happens, right? If two vectors are, so if you have two vectors, both of, let's say, the same length, when is the inner product maximized? When they're exactly the same, or yeah, when they're exactly the same, correct? And when is it minimum? When they're in opposite direction, right? Because it can go negative. Again, polynomial. Let's take the polynomial kernel. When do you think for a given, let's say, magnitude? So this is anyway a function of the inner product, right? It's a monotone function of the inner product, right? So so essentially all the properties of the inner product in RD also carry forward to this polynomial kernel. What about the Gaussian kernel? Again, it's pretty much the same, because again, this is just a function of the norms of x and x prime and the inner product. But the key difference is that for the Gaussian kernel, when x and x prime are really close to each other, no matter what their magnitudes are, as long as they're very, very close to each other, the k of x prime is something that is close to 1. It can't exceed 1. But when x and x prime are really far apart in Euclidean distance, the Gaussian kernel takes a very small value, right? Something close to 0. So the Gaussian kernel measures a different kind of similarity compared to the cosine similarity or the inner product. Okay. For the inner product, if you take the inner product, the inner product is minimized when the two vectors are in the opposite direction, right? for the Gaussian kernel, k of x prime is small if x and x prime are far apart in Euclidean distance. Right? The same holds true for the sequence mismatch kernel. If two sequences are identical, then basically you take any subsequence that's a common subsequence. Right? But on the other hand, if they're very different, let's say you take the following two subsequences, there are no common subsequences at all. Okay. So here the homework. So let's consider kx prime to be equal to indicator, the two norm between x and x prime, or the distance between x and x prime to be less than or equal to 1. It's a kernel, right? Because it's a function from Rd cross Rd to R. It takes only two values, either 0 or 1. So find whether this is a PDS kernel or not. Okay. So right now I haven't shown that the Gaussian kernel is PDS. So in general, if someone just gives you a kernel, how do you find whether that particular kernel is PDS or not? I'm sorry? Is that even feasible? Not, right? So suppose, so we'll start with some very basic properties. Suppose I have some function from the domain. This domain could be an arbitrary set to R. And let's look at the following kernel x prime to be equal to f of x times f of x prime. Okay, so essentially it's any kernel that is kind of separable. Right? I claim that this is PDS. Why? F can be any arbitrary. How do you go about showing this? Okay, first, is it symmetric? It is, because if you look at the Gram matrix, K I J, this is just f of xi, f of xj, so kji is also equal to this. Because it's just f of xj times f of xi. Right? Okay. Okay. Yeah, so u is what? So it's basically just the vector f of x1 up to f of x m transpose column vector. Yeah. U transpose.
IJ's entry would
be exactly this. So in fact, your K is just UU transpose. So this is is symmetric and PSD. What are the eigenvalues? No. Okay, what are the easy eigenvalues of this? Yeah, they're going to be m minus 1 zeros. There's one non-zero eigenvalue. What is that going to be? Summation? No. In terms of u, what is it going to be? Trace of Kij, okay, which is what? Yeah, just 2 norm of u the whole square. Right. Which is nothing but summation f of xi square, summation overall. Which one? Again, two different ways. One is either you know that there are m minus 1 zeros, right? M minus 1 this is a rank 1 matrix. So the m minus 1 eigenvalues are 0, and the trace is equal to the sum of the eigenvalues, which is equal to the only non-zero eigenvalue. That's one way. The other way is, okay, it's symmetric PSD, maximum overall x with norm 1, x transpose kx is going to be equal to the eigenvalue, right? And that you can just verify that is maximized when you take x to be u by norm u, because it's just u transpose x the whole square. In fact, that's another way of verifying that it's symmetric PSD. X transpose kx is simply equal to u transpose x the whole square, which is always non-negative. U is in fact the eigenvector, and the 2 norm of u is the corresponding 2 norm of u the whole square is the corresponding eigenvalue. I'm sorry? That k is equal to u transpose. You're okay with this, right? That by definition it means that it is PDS, right? So for every m, this holds true for every single m, and therefore k is PDS, because the graph matrix is symmetric PSD for every m, for every x1 through xn. Right? This statement is independent of the value of m and which m points you choose. Okay, so now, so this sort of gives a simple way of identifying whether a given kernel is PDS or not. Suppose we're given two different PDS kernels. Is there a way of combining them to get another PDS kernel? This basically says that if I'm given two PDS kernels, then the sum of these two kernels is also PDS, the product is also PDS, and scaling any kernel by a positive value also gives me a PDS kernel. Right? Okay, why is the first statement true? Correct. Basically, it just follows from the fact that the gram matrices corresponding to K1 and K2 are positive semi-definite, and sum of two positive semi-definite matrices is always positive semi-definite. In fact, any non-negative linear combination of positive semi-definite matrices is also positive semi-definite. It's exactly the same as you said. We'll see why. So firstly, if it is not PDS, if the corresponding matrix is not positive semi-definite, then it will not correspond to an inner product. Right? Because if it does actually correspond to an inner product, then the gram matrix must be positive semi-definite. Right? So that's a basic requirement, that the gram matrix is always positive semi-definite, because only then can it correspond to some inner product. It doesn't mean that it is sufficient for it to correspond to an inner product. Right? It's necessary, but at the moment it doesn't seem that it is sufficient. No, we're not. So we really want that K to look like an inner product, to correspond to some inner product in some higher dimensional space. Which one? So we'll make it a little more formal as we go along. But essentially what we want is that K of x prime should correspond to the inner product between some psi of x and psi of x prime for some psi. Right? Because ultimately we want to train a linear classifier in some space, some feature space, even though we may not know explicitly what the feature map is. Is that okay? Okay. So K1 plus K2 is PDS, and alpha times K1 is also PDS. Why is K1 times K2 PDS? Yeah. Okay. So let's suppose that K of x prime is K1 of x prime times K2 of x prime. So what is the gram matrix corresponding to K in terms of the gram matrices corresponding to K1 and K2? No. No. Okay, so this is how I'm defining the kernel, right? K of xx prime is equal to k1 of xx prime times k2 of xx prime. So what is the gram matrix corresponding to k in terms of the gram matrices corresponding to k1 and k2? It's just the element-wise product of the gram matrices for k1 and k2. If you're given two symmetric PSD matrices, what can you say about the element-wise product of those two PSD matrices? Have you seen this before? Okay, so I'll again leave that as an exercise. It's a very interesting result. If A and B are symmetric PSD, then their element-wise product is also symmetric PSD. Exercise. Right? So in fact, one way is through the eigen. One way of proving this is through the eigen decompositions of A and B. Okay. So now let's go back to some of the kernels that we've seen previously. The linear kernel, as we know, is a valid PDS kernel, but let's revisit the polynomial kernel. We know that it's PDS, but let's try to prove that it is PDS using the properties that we've seen. I'm sorry? Correct. No, definitely not. I mean, in all of these, for example, here K1 and K2 must be PDS, or K1 plus K2 to be PDS. It's prime whole to the power P. Just using the properties that we have seen, how do we prove that this is PDS? Binomial expansion is one way, but any other way without using the binomial expansion. So first, xx prime is a PDS kernel. What about 1 plus xx prime? Why? Which property are you going to use? K1 plus K2. 1 is a PDS kernel because it's a trivial kernel, and xx prime is a PDS kernel. So the sum is also a PDS kernel. And this whole raised to the power P is just multiplying P or P minus 1 or combining, so combining P PDS kernels. Okay, what about the Gaussian kernel? K of xx prime. Let's So that's e to the power minus x prime square by 2 sigma square. I can write this as e to the power minus norm x square by 2 sigma square e to the power norm x prime square by 2 sigma square times e to the power minus inner product between x prime by 2 sigma square. Okay. So first, is the product of these two a PDS kernel? It is, because this is simply f of x, this is f of x prime, f is some arbitrary function. So the product of these is also a PDS kernel, right? If I'm able to show that this is a PDS kernel, then the product of this and this should also be a PDS kernel, correct? Okay, e to the power minus x prime by 2 sigma square. What is the Taylor series expansion? Prime whole to the power I by factor. Right. Now again, it's a non-negative sum, but it's not exactly a sum, it's a series. So there's a subtlety over here, because it's not a sum of finitely many PDS kernels. So you need another convergence result, and as it turns out, it is in fact true. And the reason is that the Gram matrix corresponding to this kernel is a series of Gram matrices, right? So basically, if I call this K, this is summation I equal to 0 to infinity alpha I Ki, where each Ki is a PSD matrix, right? Whatever it is, I'm summing up infinitely many PSD matrices, taking some linear combination of infinitely many PSD matrices. Each alpha I is non-negative, right? The point is that this is also a valid PSD matrix, and that follows because the set of all PSD matrices is closed. So as long as the right hand side converges, it will converge to a valid PSD matrix. Again, a technicality, but any convergent series of PSD matrices is also a valid PSD matrix, and therefore any convergent series of PDS kernels is also a valid PDS kernel. All right. Again, just some basic concepts in analysis, so that's okay. All right. So therefore, the Gaussian kernel is also PDS. Any questions? Not, we'll just stop here.